Hi guys, it's your science teacher here, back with another video. This time I'm going to go through my predictions for the 2022 AQA physics paper. Now I just want to stress as well that these are my predictions and they might not all come up, but I'm going off the AQA document of the key topics they say will be assessed, the required practicals, and I've not included topics that they said definitely will not get assessed on this paper. So let's look at where I got my information from. I just got it from the AQA website, where they have included what topics will be key focuses of the exam and things that won't be assessed in the paper. Now, looking at this, what kind of stands out straight away is there's not going to be that much on electricity or radioactivity in the paper. So these are things that I've not talked about in as much detail. Also, I think they've given a bit more away for what's going to be on the foundation paper rather than the higher. So the first half of the video, I'm going to go through the overlapping topics that are on the higher and foundation. At the end, there's just a little bit extra for those foundation pupils because it says that it is going to include some of the stuff on radioactivity. Let's get started on some things that are definitely going to be included in the paper, and these are the required practicals. And the first one that I'm going to talk about is the density required practical. Now, density is how much mass is in a certain amount of volume. So to work out density, you just do the mass divided by the volume. I like putting them in triangles, these equations, so they're easier to rearrange. And the units for my different parameters in this equation, mass is measured in kilograms, density is measured in kilograms per meters cubed, and volume is measured in meters cubed. Now, one thing they might do in order to try and trick you is they might put your units for density in grams per centimeters cubed or grams per decimeters cubed. So you have to know how to interconvert between these. Now, measuring the density of regular shapes is quite easy because it's quite easy to calculate their volume. For example, this cube has a length of 2 centimeters, a width of 2 centimeters, and a height of 2 centimeters. So to calculate its volume, it's just simply 2 times by 2 times by 2. And it will have a volume of 8 centimeters cubed. Now, if it has a mass of 1 kilogram, then you could work out its density by simply doing its mass, which is 1 kilogram, divided by 8 centimeters cubed. Now, I know earlier I said you could do it in kilograms meters cubed. You could also do it in kilograms centimeters cubed, as long as you state the units that you are measuring your density in. So this box would just have a density of 0.125, which is 1/8 kilograms per centimeters cubed. However, what happens if we have an object which isn't a regular shape? For example, a rock that would have a shape something like this. How would I calculate its density? Because I can't calculate its volume by just simply doing length times width times height. Well, I have to use Galileo's principle in order to calculate its volume. And Galileo's principle is the volume of water displaced equals the volume of object. So what I could do in order to calculate its volume is place my object inside this measuring cylinder and measure the initial volume of the water here, which is around 100 centimeters cubed. When I put it into the water, it's going to rise. And say it rose to 200 centimeters cubed, I would know that the volume of my object is 100 centimeters cubed. There is another way of measuring the volume of the object as well, other than just using a measuring cylinder. We can use something called a eureka can. And what we do with a eureka can is we place our irregularly shaped object inside of the eureka can filled up with water, and what will happen is the water will overflow into a measuring cylinder and we can measure the volume of water displaced. And measuring the mass of the object will always be quite easy, and what you should use is just a top pan balance, and that's what we can use to accurately find the mass of the object. Now, the reason why we use water in this experiment is it's quite easy, and we only can use objects denser than water for this practical, because if they're not denser than water, then what will happen is they'll simply just float and you'll get an inaccurate measurement for the volume. Now, the other required practical it says that's definitely going to be included is investigating the insulation properties of different materials. Now, every time that you do the practical, if you're doing this, the independent variable will stay the same. You're changing the type of material. Now, the dependent variable, the thing that you're going to measure in order to show which material is the best insulator, is the temperature of, it could be water in there that you're measuring, that you're trying to keep warm, or it could be something else, it could be a metal block, it doesn't really matter. And in this practical, you're going to have quite a few control variables. You're going to have to make sure that you keep the same thickness of insulating material. Also, the same starting temperature of the water or the object. And there's also things in the practical to make sure that you have accurate results. For example, here you can see that I've added a lid onto the top to make sure that no heat exits and no extra heat enters our system. Now, the key to being the best insulating material will be the one that keeps the water or object the hottest. Now, the way we'll measure that is we will have the starting temperature minus the end temperature. And the one which has the lowest value for this will be the best insulator. You can also make this setup a bit more accurate by changing from having a normal thermometer to using a digital thermometer with a data logger. This would make the resolution of your equipment better, and you're more likely to get closer to the true value and be more accurate. Now, later in the video, we are going to look at energy transfers by heating in a bit more detail. So I'm not going to go into the theory behind this experiment too much yet. And you'll see why, because I'm going to talk about things like insulation in houses and what makes a good insulating material. So now I'm going to get on to the actual content in the exams as well as the required practicals. And the first thing that we're going to look at is the conservation of energy and the different energy stores there are. Now, it's really important to understand what we actually mean by this term conservation of energy. Conservation of energy is basically the principle that energy cannot be created or destroyed, but it can only change its form. So let's have a look at some of these energy stores where energy can be interconverted between these different energy stores. And the first one is thermal energy. Now, you know what thermal energy is. If I increase the temperature of something, it's going to have more thermal energy as the particles move around faster. And the first one is thermal energy. This is energy given out in the form of heat. After that, we have sound energy. We also have nuclear energy here. We have chemical energy. Don't be confused by chemical energy. It encompasses a lot of different objects, store chemical energy. For example, batteries are an example of chemical energy because it's chemicals that causes the potential difference, and that is then transferred to electrical energy. Also, we have chemical energy inside of us because when we eat food, it's chemical reactions, isn't it, that break down our food and turn it into energy. Underneath that, we have electrostatic energy, and here I've got a picture of an atom because atoms are a great example of electrostatic energy. You've got the positively charged protons which are attracted to the negatively charged electrons, and this is electrostatic forces of attraction that keep the electrons in orbit. Underneath, I've got an example of kinetic energy, and kinetic energy is just anything that is moving. Gravitational energy is due to an object's position in a gravitational field. The higher up an object, the more work is being done against gravity. So this is gravitational energy. Just think about it. If you lift up an object and then you drop it, it falls down to the earth. Underneath that, I have electrical energy. And beneath that, I have electromagnetic energy, but here I've just got a picture of a light bulb, so I'm just going to put light energy. I don't think they'll talk about the different electromagnetic waves that could be emitted. Now let's have a look at a couple of energy transfers in closed systems. And a closed system just means that energy cannot leave or enter. And there's a reason why we observe closed systems, because we're not factoring in the dissipation of energy into our surroundings. Now, energy transfers can be transferred by 4 different types of energy pathway. They are mechanical, which involves putting a force on an object. We have electrical. We also have heating, and we also have radiation. Let's have a look at 2 different examples and the energy transfers that take place. For example, here we've got a radio. Now, in a radio, we are converting electrical energy into our useful energy, which is sound. However, with a radio, you will get some wasted energy as well, which is usually in the form of heat. Most electrical appliances give out heat, and this is called our wasted energy, as it's not what we want coming from our appliance. Now, due to the conservation of energy, if 100 joules of electrical energy is supplied to my radio, then 100 joules of energy in total must come out. So if 80 joules comes out of sound, I know that 20 joules must be wasted as heat energy. Now, the energy pathway that this is followed, this is an electrical pathway. The energy transfer has taken place. Here I've got a car as well, and cars most often than not run off petrol or diesel, and this is an example of a chemical energy store. Now, what we do with this chemical energy is we burn it and we convert our chemical energy into kinetic, and also it's going to give out a little bit of wasted heat and sound. Now, it gives out heat due to friction, which would be the energy pathway of mechanical, because it's a force on the car. Same with the sound and the kinetic energy. But there is also following the energy pathway of heating as well, because we heat up our petrol or our diesel in order to provide that kinetic energy. Now, how much of our energy input converted to useful energy is known as efficiency. So the efficiency equals useful output divided by total input. So the efficiency of this radio would simply just be 80 joules divided by 100 joules, which is 0.8. And you can put it into a percentage, which would be 80%. We can represent energy transfers using a Sankey diagram. And a Sankey diagram is a to scale diagram of the energy transfers taking place. For example, this could be for a light bulb. Now, in a light bulb, our electrical energy goes in, and just for simplicity, we'll just say 100 joules of electrical energy went in. And if I was drawing it to scale, 100 joules could be represented as 1 centimeter equals 10 joules. So this would be 10 centimeters to scale. Now, let's have a look at my useful and my wasted energy. Now, my useful energy coming out of a light bulb is light, and here you can see the light energy is a little bit thinner, so I'm going to say 45 joules comes out as light, and that would be represented by 4.5 centimeters, and then 55 joules must be wasted as heat, and to draw that would be 5.5 centimeters. The reason why we use Sankey diagrams is because we can visually see how efficient an appliance is. It's really quick and easy to see which one is the most useful by which one has the thickest arrow representing the useful energy. We're now going to have a look at some of the energy stores in a bit more detail and equations used to calculate some of these different stores of energy. So let's start off with gravitational potential energy. I'm just going to represent that with capital E and then a lowercase p, just like that. And gravitational energy is equal to mass times by gravity times by height. So I can see using this triangle how I could rearrange to get to my other parameters. For example, if I wanted to calculate mass, I could just cover up mass, and mass would equal the gravitational energy divided by gravity times by height. Now, it is important to know the units of all of these as well. For example, energy is always measured in joules, mass is in kilograms, gravity is newtons per kilogram, and the value on Earth is 9.8 newtons per kilogram. It might say in an exam to use 10, but usually it uses this value of 9.8, and height is measured in meters. Now, the only thing that they can really trick you on with gravitational energy is you've got to remember that it is the vertical height you're measuring. So if someone, for example, is stood on a cliff, and that cliff is 51 meters, here the length is 51 meters. The only thing that matters is this vertical height here, which is 30 meters, for example. You might have to use trigonometry in order to work out vertical height, but you've just got to remember it's the vertical height that's important. The next one we're going to look at is kinetic energy, and the way to work out kinetic energy is by doing a half times by mass times by velocity squared. Now this one's a little bit more tricky in order to rearrange. Kinetic energy is obviously easy, half times mass times velocity squared. However, what happens if I want to calculate mass? So I'll just cover up mass, and EK divided by half times by V squared equals mass. But what about with V? Because I've got V squared, but I haven't got V. Now, in order to calculate V, what you'd have to do is you first work out V squared, which is, if I cover it up, EK divided by a half times by mass. And then what I need to do is to get rid of my squared is I square root. So V equals the square root of the kinetic energy divided by a half times by mass. Now, because of the fact that they give you the equations in this year's exam, I think there'll be a lot of rearranging that you'll have to do. And I think you'll have to do a lot of this, of looking at an equation and then turning it into a triangle and then working out what you actually have to get from your question. And that's why I'm showing you how to use these triangles in such detail. And then the final energy store we're going to look at is elastic energy, which is the energy stored when you either stretch or you compress something, and that equals half times by spring constant, which is K, times by extension, which I'm representing with X. Now, if I look at the units for K and X, because they're new, K is measured in newtons per meter, extension is measured in meters, elastic energy, of course, measured in joules. Now, it's really important as well for the extension. To get your extension, what you need to do is you need to do the new length minus the original length, and that will give you the extension. The rearrangements are very similar to with a kinetic energy equation as well, so I'm not going to go through them. But what I will do, in fact, is go through what happens when you stretch a spring. And what happens when you stretch a spring is as you add force, that spring extends. Now, that happens up until a certain point. This is called the limit of proportionality, where your spring stops behaving elastically. And they might ask about that, and that's why I just included it. And sometimes they ask you to calculate the spring constant of your spring, and for that you need to know that F equals Kx, so K equals F divided by X, and there you could calculate the spring constant and therefore calculate your elastic energy. Now, something I think they will also do in your exam for the higher tier pupils is they will combine equations and hope that you are able to make assumptions. And here's an example of a question in which you need to use two equations in order to calculate your answer. And you need to know about the transfer of energy between different stores. Now, the way I always do an equation question is I write out what I know first. Here it says that an arrow is shot vertically up in grown-ups as adults play a game of arrow chicken. If the arrow is 0.8 kilograms and is shot vertically upwards with an initial speed of 21 meters per second, calculate the height the arrow will reach. And what assumptions did I make? So, I know that my mass is 0.8 kilograms. And I know my speed or velocity equals 21 meters per second. And the height of the arrow is what I'm going to try and work out. Now, first thing to think about is maybe what energy transfers are going to take place here. So I've got elastic energy from my arrow, which is going to be converted to kinetic energy as I shoot the arrow. And then that kinetic energy is going to go all the way into gravitational energy. Now, I know the mass and the velocity of my arrow, so I can therefore calculate the kinetic energy as kinetic energy equals a half times by mass times by velocity squared. So if I do a half times by 0.8 kilograms times by 21 meters per second squared, I can get my kinetic energy, which is 176.4 joules. Now, because my kinetic energy is being converted to gravitational energy, I now know my gravitational energy as well, which is 176.4 joules. And simply I'm just saying that my kinetic energy is equal to my potential energy here. And if I look at my triangle from earlier, my gravitational energy is equal to mass times gravity times by height. And this time I'm trying to work out height. So my height is equal to 176.4 joules divided by gravity, which we say we know is 9.8 newtons per kilogram times by the mass, which is 0.8 kilograms. And that will give me an answer of 22.5 meters. Now, what I always do with these equation questions as well is I underline my final answer if there's lots of steps, and I circle my unit just to show to the examiner, look, this is my answer. Look, I've included my unit, so there's no excuses for them not to give you full marks. When energy has been transferred from one store to another, we say that work has been done on that object. And we can calculate the amount of work done using the formula work equals force times distance. And because work is just the amount of energy transferred, work is measured in joules, force is measured in newtons, and distance is measured in meters. So if we go over here and look at this example question, it says a horizontal force of 70 newtons has been acted on, and it's moved the toy car a distance of 20 meters. So if I write in what I know, force is 70 newtons, the distance is 20 meters, and if I want to calculate my work done, all I do is times them two together, which will give me 1,400 joules. Now, in this question, it also says what is the power as well, and to work out the power, you need to factor in the time it takes as well, which is 10 seconds, and we're working out the power. That's my question mark. And if I go over here to this triangle, what is the equation for power? Power is energy divided by time. So now I have the energy, which is 1,400 joules. And if I divide it by 10 seconds, I will get 140 watts. So power, just simply the definition of power is how quickly the energy is transferred. And like I said earlier, I think because of the fact they give you the equations, I think a lot of the time what they're going to do is things like this, where they want you to apply multiple equations in order to get your answer. And when I've got my final answer, I circle my unit, underline my answer just like that. And just going over here, power, the unit is watts, time is seconds, and energy obviously in joules. Now I use this energy energy is exactly the same as work done. So that's why I just use the value of 1,400 from up here in this equation. The next thing we're going to talk about is something called internal energy. And to look at internal energy, I'm going to draw the three particle models for the three states of matter. And if you look at a solid, in a solid, all the particles are touching and they are in nice, neat rows and columns, just like this. Now, when I'm drawing these particle models, I'm really careful to try and I know I don't do it perfectly, but try and keep my particles a similar size. And when I go to a liquid, the particles are no longer in rows and columns, however, they are still touching. And then in a gas, my particles are no longer touching and they are free to move. Now we need to know what the changes of state are called as well, and going from a solid to a liquid, that is called melting, and going from a liquid back to a solid, that's called freezing. From a liquid to a gas is called evaporating, and going from a gas to a liquid, and you'll see this if you blow on glasses, you get what's called condensation. Up here I have a definition of internal energy, which is the total amount of kinetic energy and potential energy of all the particles in the system. Now, going through my different states of matter, the total amount of internal energy stays the same. And I know you might think that's weird because of the fact as I go from a solid to liquid, the particles are more freer to move, so they have more kinetic energy. And going from a liquid to a gas, well, they certainly have more kinetic energy because the particles are free to move. However, the internal energy of the system stays the same throughout all of them because of conservation of energy. And that's where this potential energy comes in. Potential energy is basically the energy through bonds. And in a solid, these have the greatest potential energy and the lowest kinetic energy. Whereas in a gas, these have the least potential energy because they have no bonds between them particles, and they have the greatest kinetic energy because they are free to move. So that's what's going on when I go through my 3 states of matter to the internal energy. And if I actually look at a heating or cooling curve, then I could see this trend being observed. For example, if I heat up a material, when it changes state, I get a flat line, and when it changes state again, I get another flat line. Now, this first change of state for my heating curve, this would be melting here, and it's requiring energy to break the bonds between my particles. Like I said, it has the most potential energy in a solid state. Now, here, going from a liquid to a gas, that requires even more energy because of the fact you go from all the particles touching to now no longer touching, and that requires lots and lots of energy. Now, going the other way and looking at a cooling curve, well, the same kind of trends observed here. I've got a large flat line and then a smaller flat line down here. And here my first one is condensation, and it requires a lot of energy to remake these bonds, just like down here. And then down here, going from a liquid to a solid as well, called freezing, I also require some energy as well. So I've just circled my changes in state just like that. Now, for your exam, I'm pretty sure something like this might come up, and you're going to have to talk about the energy changes involved going from different states and the internal energy going from different states as well. You can actually calculate the amount of energy required for a state change using what's called the specific latent heat. And the equation to calculate that is that energy equals the mass times by the latent heat, where energy is obviously measured in joules, mass in kilograms, and latent heat in joules per kilogram. Now, what latent heat actually is, if you want the definition, is latent heat is the energy required to change the state of 1 kilogram of substance. Now, there is 2 latent heats. There is the latent heat of vaporization, which is going from a liquid to gas or gas to liquid. And there is also the latent heat of fusion, and the latent heat of fusion is going from solid to liquid or liquid to solid. Down here, I've just drawn a quick practical setup of how you could calculate the specific latent heat of fusion of some ice here. So here I've got a heater, I've got a joule meter, and I have a power source here. This just means AC power source. And when the heater is switched on, it's going to cause the ice to melt, and the ice is going to melt down here onto a beaker that's on top of a balance. So I can calculate the mass of water that I'm making, which can go into my equation. And I've also got a joule meter here measuring the energy, and if I do the energy divided by the mass, that will give me the latent heat. Now, I could also do the same to get the vaporization. The only difference would be this time, instead of putting my heater inside ice, I'd put heater inside water, and I could measure the amount of water lost that way. Now, investigating energy transfers through heating is very important because of the fact it affects the way that we insulate our homes. And heat can be lost in 3 ways. There's one which is called conduction, which is through direct contact. This is just heat transfers by direct contact. And you've probably observed conduction many times when you have put a spoon in a hot cup of tea, and the spoon has got hot when you touch the top of it, even though the spoon isn't fully submerged in the water, that's because the heat has passed through the whole of that spoon, because metals are fantastic conductors of heat. There is also convection, and convection basically happens in fluids. And what happens in your fluids is when something gets heated up, it becomes less dense and therefore it rises. And once it's risen, it will cool down again and become more dense and therefore fall. And this method of heat transfer happens under the earth. In fact, there are convection currents underneath our earth which cause our tectonic plates to move around. Convection also happens in radiators. That's how your radiators heat up the home. Is the water gets heated up, it rises up your radiator and then falls back down as it cools down. And then we have radiation, and radiation can travel through even a vacuum. You've probably heard of infrared radiation. Infrared radiation is just heat. Every object above 0 Kelvin or minus 273 degrees C emits some infrared radiation which travels out and disperses. So let's have a look at our home and how we can insulate it to make sure we minimize the amount of heat escaping from our house. And there's a few things we do. The first we do is we install what's called double glazing windows. And double glazing windows are perfectly adapted for their function by having an air gap. And basically what that air gap does is air is an incredibly poor conductor of heat. So the heat cannot travel between the two panes of glass, and therefore our home stays nice and warm. We also have what's called cavity wall insulation. And cavity wall insulation, basically what it does is it's a foam-like substance, and it stops convection currents from forming between your walls. And we also have loft insulation as well. And you've probably been in your loft before and you've noticed that really itchy material that sometimes gets on your skin. It's not very nice to have on yourself, and it's not nice to breathe in either. And loft insulation is adapted by having lots of air gaps, just like with this double glazing window. It's quite a spongy material, isn't it? And the heat cannot travel all the way through it. You can measure how good of a conductor of heat a material is by something called its specific heat capacity. And the equation you need to know for this is energy equals mass times by specific heat capacity times by the change in temperature, where energy is of course measured in joules, the change in temperature is measured in degrees C, specific heat capacity in joules per kilogram degrees C, and the mass is measured in kilograms. And specific heat capacity can just be defined as the amount of energy required to raise 1 kilogram of substance by 1 degree Celsius. So let's look at an example question and how we might go about rearranging one of these questions. It says calculate the final temperature of 150 grams of water. So I know my mass, which is 150 grams. Now, if I go over here and I look, mass is measured in kilograms. That's my base unit for mass. So I need to convert this into kilograms. There's a little win in an exam as well, because you might just get a mark for doing a correct conversion. So that's 0.15 kilograms. I know my specific heat capacity, which is 4,200 joules per kilogram degrees C, because it's water. I know my energy, which equals 2.6 times 10 to the 4 joules. And I know my initial temperature, but I don't know my final temperature. So I don't really know my change in temperature yet. This is what I'm going to have to work out, and then I can use my initial temperature here in the final bit of the question. So let's see how I'm going to work this out. So if I cover up my change in temperature here, my change in temperature equals the energy, which is 2.6 times 10 to the 4 joules, divided by my mass, which is 0.15 kg, times by the specific heat capacity, which is 4,200 joules per kilogram degrees C. And that equals 41.2698. And that's not a very nice way to leave that, so I'm going to actually round it. Now, if I look at my question, I have 3 significant figures in my question, so let's use 3 significant figures. 41.3 would be my change in temperature. And then now I can calculate my final temperature by adding it to my 19 degrees C. So just an easy calculation to finish, plus 41.3. And that gives us 60.3 degrees C. And I'm going to circle my unit and underline my answer. If you are doing higher tier, well done, you have finished today's video. If you are doing foundation, there is just a little bit just to keep going, and we're just going to go over electricity and radioactivity really quickly and some of the things that could come up on the foundation but not the higher tier. And that is current charge and potential difference. That was something that it says is a bullet point on foundation but not higher. And you need to know what all of the different ones are. Now, I like to think of electricity like a river flowing, and what pushes the river down the hill is how steep that hill is, and that's kind of like the voltage in my circuit. The voltage is known as the push of charge. Now, in a river also you have what's called a current, and the current is how much water passes per second, whereas in a circuit, the current is the amount of charge passing per second. Also, in a river, you come up with some obstacles, and this is the resistance. Now, in a river, you're going to have things like rocks that are going to stop the water from flowing. Now, in a circuit, what you might have is you might have a light bulb, for example, which has a really high resistance wire in, which means lots of metal ions for them charged particles to bump into, and this is just the opposition to the flow of charge. And there's also some key equations you need to know to link these. For example, the first one is the Ohm's law equation. And Ohm's law is that resistance equals voltage divided by current. Now, voltage is measured in volts, current is measured in amps, and resistance is measured in a weird symbol called ohms. Also, from the definition of current, you can come up with a little equation as well, because we know that the current is the amount of charge passing per second. You can get yourself a little triangle here, and you know that I equals Q divided by T, and Q is the charge, which is measured in coulombs, T is the time in seconds, and I obviously is the current measured in amps. The next thing I'm going to do is talk about static electricity and making that charge move. Now, things can become positively or negatively charged by rubbing two materials together. Now, if they've got a positive charge, we draw an arrow going away from positive charge, and for a negative charge, we draw an arrow going into my negative charge. Now, to make something charged, I can rub electrons onto a material, which takes electrons away from one of the materials and puts them onto another. For example, if I used a rod and a duster, and I rub that duster on my rod, what's going to happen to my duster is it's going to rub electrons off the rod, and they're going to go onto the duster, and this is going to make this positively charged and this negatively charged. Now, what I could observe is if I put them close together, they're going to now attract due to the fact they're going to be oppositely charged. And if I put them by the same charged object, then what would happen would they would repel each other. And the last thing I'm going to do is just talk about the changes in the nucleus of what happens during radioactive decay. And there are three types of decay. There are alpha decay, beta decay, and there is also gamma decay. Now, in alpha decay, what happens is you emit a helium nuclei. And what this does is this reduces the atomic number by 2, changing the element. Here I've gone from radium to radon, and the atomic mass goes down by 4 due to helium having an atomic mass of 4. In beta decay, it's a little bit different. What happens in your nucleus is a neutron turns into a proton, and also you emit a high energy electron. So what actually I can see and observe here is my iodine has changed to xenon because my atomic number has gone up by 1. Nothing has happened to my atomic mass. And for my beta particle, you just need to remember at the bottom number, my atomic number is -1 and the atomic mass is 0. Now, in gamma decay, nothing actually happens to my nucleus. It's just the emission of a high energy wave. Due to the fact that they're all emitting different particles, they have different properties. For example, alpha is the most ionizing, meaning that it can ionize atoms in the air, and this means that it doesn't travel very far. Beta, however, is a bit more ionizing, a bit more penetrating, but not as ionizing. And gamma is the most penetrating and the least ionizing of all three types of radiation. Now, I really hope you have enjoyed today's video. Remember, if you do want to go into any of the other topics in more detail, please do check out my channel. And if you did like today's video, please drop it a like and subscribe to the channel.